In this video, we'll look at solving square root functions. There are two cases that we need to think about. The first case is to solve for y if we're given x, and the second case is to solve for x if we're given y. So let's look at this first example over here. We're given the function y equals 2 times the square root of 3x plus 4 plus 2, and we're asked to find y when x equals 4. So to do that, we simply replace the x in our original function with the value of x that we're given. So in this case, we'll have y equals 2 times the square root of 3. Now instead of writing this x, we'll write the value, which is 4. So 3 times 4 plus 4, and then we have a plus 2. And now we can combine terms and solve. So y equals 2 times the square root of 3 times 4 is 12. We still have our plus 4, and then we have a plus 2. So y equals 2 times the square root of 12 plus 4 is 16, plus 2. Y equals 2, the square root of 16 is 4, so times 4 plus 2. And remember here, when we're taking the square root of 16, we are only taking the positive root. So we only need to worry about the times a positive 4. We don't have to worry about the fact that negative 4 is also a square root of 16. This will be the case for all of our square root functions. We will only ever take the positive root. We can finish solving this. Y equals 2 times 4 is 8, plus 2, so y equals 10. And there's our answer. Find y when x equals 4, y is 10. So the first case, to solve for y when we're given x, is fairly straightforward. Our other example is to solve for x if we're given y. Now when we're given y, we might be given a numerical value of y, such as y equals 2 or y equals 5, or we might be asked to find the zero of their function. That simply means when y is 0. Or we'll be given two different functions and asked to find where they intersect. So in this case, we're asked to find where these two functions cross each other. What we mean is when f of x equals g of x. So we can rewrite our equation from f of x equals g of x to substituting in what f of x is and what g of x is. So we can write 3 times the square root of 2x minus 3 plus 4 equals g of x is 2x plus 1. Now what we're going to do, or the first thing that we need to do, is we have to isolate the radical. That means we want what's under our square root sign to be on one side of the equal sign and everything else on the other. So let's subtract 4 from both sides. We'll end up with 3 times the square root of 2x minus 3 equals 2x minus 3. We've subtracted 4 from both sides. And now let's divide everything by 3. We'll be left with the square root of 2x minus 3 equals 2x minus 3 divided by 3. What we also need to do is we have to do something called state our restrictions. So if our first step is to isolate the radical, our second step is to state our restrictions. I typically do this off to the side. What we mean by stating our restrictions is simply that what's under our square root sign has to be greater than or equal to 0. It cannot be negative because we can't take the square root of a negative number. So our restriction is 2x minus 3, because that's what's under our square root sign, has to be greater than or equal to 0. And we'll solve for x. So 2x has to be greater than or equal to 3, and x has to be greater than or equal to 3 over 2, or 1.5. And this is just something that we're going to remember for later when we have our answers. So after we've stated our restrictions, we can come back over here and continue solving for x. So our third step here is to solve 4x. If we square both sides, that'll get rid of our square root sign. So let's do that. We'll end up with 2x minus 3 equals 2x minus 3 over 3, all of this squared. And if we square that, we'll end up with 2x minus 3 equals 2x minus 3 times 2x minus 3, all over 3 squared. So 2x minus 3 equals 4x squared minus 6x plus 9. I've simply used FOIL on these top brackets. Divided by 3 squared is 9. What we want to do at this point is we'll notice that we have a quadratic. To solve a quadratic, think back to last year, we need to set the whole thing equal to 0, and then either factor or use the quadratic formula. So let's get everything on one side, and let's eliminate this fraction while we're at it. We'll multiply everything by 9. So we'll have 9 times 2x minus 3 equals 4x squared minus 6x plus 9. We'll have 18x minus 27 equals 4x squared minus 12x plus 9. If we subtract 18x and add 27, we'll end up with 0 equals 4x squared. Negative 12x minus 18x is a negative 30x. And a positive 9 plus 27 is a plus 36. So at this point, we can either factor or we can use the quadratic formula, depending on your comfort level with factoring. Let's use the quadratic formula just as a reminder of what that looks like. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So x equals negative b is a positive 30 plus or minus the square root of negative 30 squared minus 4 times a is 4 times c is 36, all divided by 2 times a is 4. So let's combine some of this. X equals 30 plus or minus the square root of 30 squared is 900 minus 4 times 36 is 576, all divided by 2 times 4 is 8. So x equals 30 plus or minus the square root of 900 minus 576 is 324, all divided by 8. So x equals 30 plus or minus the square root of 324 is 18, all divided by 8. If we do 30 plus 18 divided by 8, we get x equals 6. And if we do 30 minus 18, all divided by 8, we'll get x equals 1.5. Now here we have two solutions, x equals 6 and x equals 1.5. It could be that these two functions cross each other twice, or it could be that one of these solutions is extraneous. To check, we have to check these against our restrictions. So x is greater than or equal to 1.5, so that one works. And 1.5 is greater than or equal to 1.5, so that one works. So we've checked it, but we aren't quite done yet. They both fit within our restrictions, but we also need to plug these back into our equation and check to make sure that we get a real answer. So to check, let's check our 6 first. We'll take our function, our very original function where f of x equals g of x, and we'll substitute in x equals 6. So 3 times the square root of 2 times 6 minus 3 plus 4 equals 2 times 6 plus 1. This is 3 times the square root of 2 times 6 is 12, minus 3 is 9, plus 4 equals 2 times 6 is 12, plus 1 is 13. The square root of 9 is 3, so 3 times 3 is 9, plus 4 is 13. We end up with 13 equals 13. So this answer, x equals 6, works. Let's also check x equals 1.5. We'll end up with 3 times the square root of 2 times 1.5 minus 3 plus 4 equals 2 times 1.5 plus 1. This becomes 3 times the square root of 2 times 1.5 is 3 minus 3 is 0 plus 4 equals 2 times 1.5 is 3 plus 1 is 4. The square root of 0 is 0. 3 times 0 is 0. So we end up with 4 equals 4. This is also a true statement. So in this case, we have two solutions, x equals 6 and x equals 1.5. If we ended up with statements that weren't true in either of these cases, right, like 13 equals 7 or 4 equals -5, we would know that that can't possibly be a solution in this case. For us, though, both of our answers worked out, and we have two solutions. Let me just show you a quick little graph over here as to why we might have extraneous solutions. And it comes back to the fact that we're only ever taking the positive root. So if we had a function, a square root function, that looked like this, and let's say that we also had a line that looked like this, and this is our f of x function, and this is our g of x function, we see that f of x and g of x only cross at one point. But that's because we've only taken the positive square root, which is what we need to do when we're looking at square root functions. However, there's an imaginary line that kind of mirrors this top one. And that's what would happen if we also took our negative root. And so we see that if we also took our negative root, there would be a solution here, but it doesn't actually exist for our square root function. That's when we have extraneous solutions, where our g of x function crosses f of x, but crosses our imaginary f of x, and not actually the function. So in this case, both of our solutions worked, which means that f of x crosses g of x twice, right? If we have our square root function, for this example, it actually crosses through the vertex and another point. That's not a great picture for you, but let's say the vertex was there, crosses through the vertex and another point. But we can see that we may have extraneous solutions in other examples. So I hope that clarifies solving square root functions.